Hello and welcome. My name is Ulf Tilstam, and I'm here to present to you that the sulfolane is a versatile and dipolar aprotic solvent that is useful for modern things like refinery industry or cleaning sour gases. The first process, I would like first to introduce you to the industrial process for the synthesis of sulfolane. That is a coupling between sulfur dioxide and butadiene at 95 degrees in isopropanol to give sulfolene, which is number 4. And after that, reduction with hydrogen and rain and nickel to get sulfolane. This is a standard industrial process that was first developed by Shell in the 1940s for the use in the oil industry. After this industrial process, I would like to show you some physicochemical data and toxicological data in comparison to DMSO, NMP, DMAC, and DMF, and to show you the usefulness in comparison to those other 4 solvents. So, as I said, sulfolane is a dipolar aprotic solvent and has comparative physicochemical properties to DMSO, NMP, DMF, and DMAC. The most important data are the relative permittivity, the dipole moment. As you can see, the dipole moment is high for sulfolane, the highest, and it is among the highest also for the relative permittivity. The Hildebrand solubility parameter is also an important parameter, as well as the normalized empirical solvent polarity parameter, where you can see in all of these cases that sulfolane is among the highest values. The only one that can compare is DMSO. So the conclusion is that sulfolane is capable of a strong solvation of cations, which is very, very important for a solvent when we use inorganic salts in reactions. And it's also very strongly solvating polarizable intermediates. The toxicological data for dipolar aprotic solvents is sulfolane has the highest toxicity in comparison to, for instance, to DMSO. Sulfolane has 1.9 grams per kilogram rat oral, and DMSO has 14 grams per kilogram. But the others like NMP, DMF, and DMAC are about the same as sulfolane. But there's a difference between all of these solvents, and that is that sulfolane has a very low skin permeability in comparison to the other ones. It's only 0.2 milligrams per square meter per hour. So the conclusion for me is that sulfolane is safer than the others to use as a reaction solvent. I have picked out some selected examples of reactions in sulfolane. Sulfolane is highly stable at elevated temperatures in comparison to DMSO, which is not that stable at high temperatures. It is also very stable against strong acids and bases, which is also important for types of reactions where, as a solvent, types of reactions where we need bases or acids at high temperatures to use a solvent that is stable. Sulfolane cannot be used at extreme reaction conditions. And so I have some examples to show you that. But sulfolane is also useful solvent under normal conditions. Although there's one drawback, and that is that the melting point is 28 degrees. But if you can use water in your reaction mixture, then 3% water in sulfolane lowers the melting point to 10 degrees. And if you add in even more water, the melting point goes down to 0 degrees. So it should be possible to run those reactions with standard equipment. First, I picked some examples on Friedel-Crafts acylations. The cyclization of the sulfate salt of 1 works very well with 12 equivalents of sulfuric acid in sulfolane for 3 hours at 70 to 75 degrees. This was reported by Gala et al. In Organic Process Research and Development some years ago. Another Friedel-Crafts acylation was also reported earlier in a patent with to form the benzoxacinone with polyphosphoric acid in combination with sulfolane, a 1-to-1 mixture at 110 degrees, and the reaction was performed for 4 hours. Takizawa et al. Also reported a similar intramolecular Friedel-Crafts acylation with polyphosphoric acid in sulfolane. This reaction took 1 hour at 110 degrees, and the reported yield was 63%. And Nelson et al. Also have used polyphosphoric acid together with sulfolane at 130 degrees for 4 hours to give also a cyclized product, a 7-membered ring. There has also been a report on Friedel-Crafts alkylation, also intramolecular. It was reported by Burdett et al. In Journal of Chemical Society in 1967. And the yield was reported to be 74% after a reaction that took 1 hour at 125 degrees. Not only acids can be used at high temperatures together with the sulfolane, also phosphorus pentachloride. And here we have a phosphorus pentachloride mediated annihilation that worked very well with phosphorus pentachloride in sulfolane at 120 degrees. The reaction is slow, and it took 14 hours, and the authors reported that this was the best system of all because others didn't give this conversion. And they obtained a 90% corrected yield. Also, phosphonylation with phosphorus trichloride has been reported, and to form the phosphonate of butyric acid, aminobutyric acid. The reaction is run at 60 degrees for 12 hours, and after workup, they got an isolated yield of 55%, and the purities was 99.9. The authors claim this to be the best solvent of all solvents due to the stability of the solvent. Also, reactions with phosphorus oxychloride has been run in sulfolane and worked very well. This very complicated Pictet-Spengler cyclization was found to be the only way to do this reaction, because they form a 7-membered ring, and the authors say that it was the best combination, and it was really worthwhile using sulfolane, because all other solvents under standard condition didn't give any conversion at all. In the best case was NMP, which gave 10% of the product. And the reaction in sulfolane was run at 80 degrees, and they obtained 51%. Also, a ring or a rearrangement of a nitroso-indole has been reported with 3 equivalents of phosphorus oxychloride in sulfolane, and here the reaction was run at 200 degrees, and it took 1 hour, and it got a 90% yield. Also here, the authors claim that this was the only solvent that could be used to run this reaction at this high temperature. Sulfolane has also been used as it is very good in dissolving, for instance, potassium fluoride. So it has been used a lot for converting chlorides on aromatic compounds into fluorides, which is a very useful conversion. And under standard condition, it is very difficult. The authors in this case first chlorosulfonated the starting material, the tris-chlorobenzene, and then converted it into the bis-fluoro with potassium fluoride in sulfolane, and the reaction was done at 195 degrees to give number 3. After that, it was hydrolyzed with sodium acetate at 80 degrees, and then the sulfonic acid would cleave off with 66% sulfuric acid at 205 degrees. Also, nitration has been done with nitronium tetrafluoroborate. This is a difficult salt to dissolve, and sulfolane seemed to be, according to the authors, very good for doing this, and the reaction was run at 80 degrees for 3 hours, and it gave a 76% yield. It's much higher than the reported ones from using other solvents. So we have been working for some years now with continuous processes, and we have developed a continuous proto-decarboxylation of heteroaromatic carboxylic acids in sulfolane. And what we use is a high-pressure syringe pump. And a coiled tube reactor, which is in an oven. At large scale, it's better to use the coiled reactor embedded into, let's say, a pressure filter filled with a liquid, so that you can transfer the heat better. And then we have a back pressure regulator to control the pressure within the reactor. And we started the decarboxylation with DBU, and for instance, various benzothiophenes could be obtained from at 300 degrees in a stainless steel tube reactor for 40. The reaction was run for 40 minutes, and the 4-bromo gave 81%, the 3-chloro gave 84%, and the benzothiophen on its own was obtained in 80% yield. We also studied the same reaction with indole to obtain indoles from the indole carboxylic acid. And with no substituent, we obtain indole in 84%. Also in this case was DBU used as the base. And the reaction took, instead of 40 minutes, it took for indoles only 20 minutes. And with the 5-methoxy, we obtained 87% yield. For the 5-chloro, we obtained 83% yield. And with the 1-methyl, we also obtained 85% yield. The reaction also works with pyridines. But in this case, we used 3% water to get the pyridine carboxylic acid dissolved in the mixture. And the reaction was also done within 20 minutes. And here we had an isolated yield of 85%. And for thiophene, it was not possible to use the base DBU. Instead, we have to shift to DAPCO, and we used one equivalent of DAPCO to obtain the thiophene at 300 degrees for after 20 minutes reaction time. We have also developed a continuous methylation of phenols and NH heteroaromatic compounds with dimethyl carbonate. And all of these reactions were also done in sulfolane. And the reaction here is much cleaner than when you use another solvent like DMAC, which has been reported in the literature, or when you use DMF as solvent. There you see much more byproducts, which means that the sulfolane is stable under the reaction conditions. We used a catalytic amount of DBU, and we used 2 equivalents of the dimethyl carbonate as the methylating agent for when we methylated different phenols. And we obtained the corresponding methylated compounds in all cases in very good yields. And we also investigated the same type of methylation for indoles, and we used also here a catalytic amount of DBU, and the reaction was run at 240 degrees. After 20 minutes, we have the N-methyl indoles in a clean reaction. Also, imidazole worked well, and here we got, after 20 minutes, an isolated yield of 90% with 2 equivalents of dimethyl carbonate. There has been a major interest over the last 5 to 10 years for 5-hydroxyindazole. It has been reported in various patents to be a very interesting starting point for various active compounds. But there has been no report on to do this clean reaction. It's very difficult to form 5-hydroxyindazole. So we have found an old paper, French paper, that claimed that if you use a lead reactor and you use diluted sulfuric acid, you can transform 5-amino-indazole to the 5-hydroxy. And we found that very interesting, so we developed this. We changed from sulfuric acid into methylene sulfonic acid, and we used aqueous sulfolane, and we ran the reaction at 250 degrees for 30 minutes, and we got a clean conversion into the 5-hydroxyindazole with an isolated yield of 86%. So, to summarize what we have found up to now concerning using sulfolane as a solvent in organic reactions is that sulfolane is a dipolar aprotic solvent. It solvates strongly cations and polarizable organics, for instance, potassium fluoride, which worked very well in that conversion in the halo exchange reactions. It is stable under extreme acidic or alkaline conditions that we have seen in various examples for batch or in continuous processes. Sulfolane is very useful for reactions with inorganic salts, potassium fluoride, strong acids, sulfuric acid, or acid chlorides like, for instance, phosphorus oxychloride. And sulfolane has also been successful as a solvent in continuous high temperature, high pressure reactions. And I would like to thank you for your interest.